Okay, it's time for us to take a look at the reference code for this guy. Okay, this is the IO define. Okay, this is the IO define of this module. Then to count for the 64 cycles, we have to define a counter inside this module. So this is a counter which will count from 0 and up to 63. So totally 64 cycles. Then you will generate the output valid signal, ZID valid. Yes. At reset, they are both 0 and at this 1 cycle pass of SOB, the ID value will be 1 and the roster count will be clear to 0. Then when the ID will be 1, the roster count will continue and 1 cycle by cycle. And when roster count equal to 63, the ID value will be assigned to 0. So can you imagine the waveform for the signal of the ID value and roster count and SOB? So from this code segment, can you draw a waveform for SOB, the ID value, and roster count? Okay. Please note that if there is just one statement after an if branch, there is no need for you to add the begin end. Yeah. Okay. There is no need for you to add the begin end. Okay. But if there is two statements or more than one statement under this condition, you have to add the begin end. And the second is, do you have to write else branch for this always block? Do we need to add the else branch? Or if we don't write the else branch to pair with the if statement, will this block generate latch? The answer is no. Okay, this is a part edge triggered always block, and we want to generate DFF. And the DFF itself has a function of memory data. Yes, it can memory data if there is no clock edge, or if the condition, the update condition is false. So the DFF itself can hold the data of last cycle. So this will, if you omit the else branch, the synthesizer will not generate latch for this code segment. That is, for sequential logic always blocks, there is no requirement of complete conditions. Okay, then you will try to use the mux, okay, to generate the ID output. Each value of roster count, you will generate the ZID value. So actually, this is the addends in this scan order. Yeah, this is the addends in raster scan order. Okay, the naming maybe some confused. So this is you can look at this is a 64 to 1 mux with 6 bits. Yes. So I think some of you may think out this architecture very quickly. That is use the mux to select the output, and you can treat this as a lookup table. Yes, you assign array value for each address, so you can treat it as a lookup table. Okay, is there any other way to implement this function? Okay, this is another way. The ID value and roster count is the same, but the output is something strange or something genius. It just exchanges the bit location of roster count. It just change the bit location of roster count to generate the ID output. So you can treat it as this is sync from algorithm. Yeah, this has deep evaluate of the algorithm of this function. So it find a simple algorithm to calculate the output. Okay. Yeah, this is something magic. Okay. I don't want to explain how to design the algorithm for this function. Okay, you can try to understand it by yourself. But I want to emphasize here is, you can say for the same function, if you use different algorithm, this will need two totally different designs. The difference is the area after synthesis, the area, the logic delays. Yes. For example, this implementation will use more area. Yeah, there is 64 to 1 mux with 6 bits. And the logic delay must be larger. Yes. Well, for this part, there is actually no logic for this statement. They just exchange the bit locations. Okay. So please note that for the same function, the different algorithm will need two totally different designs with different PPA, power performance area. Okay, let's take a look at the test bench. The head of test bench is usual. Okay, just generate clock, save the waveform. Then we will use the initial block to generate the input signal. That is the SOB and the just SOB. So you can read it. There is nothing special, and we just want to generate the sequence we are interested, such as the back-to-back, the 1T wait cycle, 2T wait cycle sequence between each block, and 3T wait cycle sequence. Okay, this syntax may be new to you. This is the for loop statement. For loop. Okay, this is something the same as this for loop in C language. Okay. This is initial assignment, and this is the condition to detect whether this loop will be executed or not. And this is the update statement after each loop. And this may be new also. This is a system call that will generate a random value. Okay. But and the return value is in the signed format, signed integer. Okay, so you can, if you want unsigned number, you can use the unsigned system call. Okay. Let's compile it and test. Okay, it seems okay. In this code segment, we will run about 1,000 tests of blocks. And with each block, the wait cycle is a random value. Yes. The value range of wait cycle is 0 to 63. So you can say the stimulus may be divided into two parts. The first part is the fixed sequence. That is, we have the fixed waveform for the input signals. And the second part is we want to generate some random sequence for the input signal. So this is basically two categories for generate stimulus, the fixed sequence and the random sequence. So, and last, we will end the simulation by calling the system function finish. Then, as we have already two implementation, yes, so we can instance the two different implementations. This one as the DUT, that is, we want to use it to do synthesis, and we can use this one as the reference model. Yes, we can assume that this model will be most likely with less bugs. We can assume this implementation will have less bugs. Yes, you just make sure the numbers you write here is the same as as the numbers in the diagram. Then, okay, this is the automatic result check part. First, we'll check the valid signal is the same or not for each cycle. Then, if the valid signal of model is 1, we will check the ZID output of model and the DUT. If there is any error, we'll display the error message, or you can even stop it. Okay, or even you can stop it. Yes. Or you can count the times of the error. For example, you can Then at this point you can yes. Okay, let's compile it again. Yes, same path. Okay. Okay, same path. Okay. Okay. Do you have any question for error count? And it was assigned in two procedural blocks. One is in the initial block. Yes. Then it will assign again in the always block. Will this cause multi-driven problem? Yeah, the answer is no, because this is just pattern. Yes, test pattern. It will just be used as simulation. We will not use it to do synthesis. So you can just follow the Verilog syntax is okay. There is no coding rules for testbench. Okay. You just follow the Verilog syntax and follow the coding rules of programming. And please code this function and simulate it at your own location. Okay, that's all for this section. Thank you.